this is a problem that machine learning has to tackle if you want to go after problems which are more general AI-like.
How possible is it, do you think, that focusing on the brain as a guide for developing general AI, that could actually limit our potential to go beyond that level of intelligence?
It doesn't, in my mind, and I explain why. So one,
this is Brain Inspired.
Hello, this is Paul Middlebrooks. You heard at the beginning there my guest today, Dileep George. Dileep co-founded Numenta with Jeff Hawkins over 10 years ago, and most recently he co-founded the company Vicarious with Scott Phoenix. So the goal of Vicarious is to build general AI robots in the long term. As you may know, I've had mostly people on the show so far whose goal is to understand the brain, but that's not Dileep's goal. But he does believe that the way to get to general AI in robots is to understand the brain. It's interesting, we talk about the model that they've developed at Vicarious that does things like breaking CAPTCHAs, as you'll hear in the show. But we go on to talk about his most recent work, putting further biological constraints on that model to map it onto what we know about how the cortex is organized, so he can have a model that functions and resembles our brains. And try as I might, I was unsuccessful getting Dileep to just hire me on the spot at the end. I'm going to keep swinging on that, though. Damn it. Occasionally, I add extra stuff into the show notes. That's the case for this episode. I link to a nice 10-minute talk that Dileep gives, summarizing some of his outlook and approaches and some of his work. So check the show notes for that and all of the other stuff that we talk about. It's at braininspired.co/podcast/13. Remember, if you have a question you think I should include for a future guest, send it my way to paul@braininspired.co. If you find value in the show, here's what I would love for you to do. Think of a person or two that you'd love to collaborate with on some AI brain-related project, and, of course, tell them about the Brain Inspired podcast. But also, I suggest that you propose with them a weekly mastermind meeting to get the ball rolling. Now, a mastermind meeting, if you don't know, is a term that's often thrown around in the entrepreneurial world. It's basically a meeting with other minds where you share your progress on things, ask for help and ideas from other members, and you help the other people where you can as well. So this was a huge tool in Andrew Carnegie's bag, for instance, and many others. And as we all know, collaboration is always the best way to go. All right, enough preaching from me. You can find Dileep on Twitter. He is at Dileep Learning. That is Dileep Learning, a very good handle. And you can learn more about his company, Vicarious. Just go to vicarious.com. Okay, here's my conversation with Dileep. All right, Dileep George, welcome to the podcast, and thanks for being here.
Thanks, Paul. Great to be here.
So, Dileep, you've been a busy person. You were the co-founder of Numenta with Jeff Hawkins, of sort of in the neuroscience world. I guess he is famous and infamous. He wrote a book called On Intelligence, which has inspired a lot of people, including me. And so you co-founded Numenta with him, and there you developed the algorithms for the hierarchical temporal memory.
Correct.
Technology that he uses, that you guys use. And actually that has recently been released as open source software, so people can go and play with it. There's even an HTM school on YouTube. So, yeah.
Okay. I didn't know about that. Those are all recent. I left Numenta in 2010, so a lot has happened there since then.
Yeah.
Definitely. So,
Right. Well, so most recently you have co-founded Vicarious, and here is what I think I know about Vicarious. So you guys are working on general AI for robots with a long-term vision in mind, and you're doing it from the perspective that it's important to understand human brains and incorporate features from neuroscience, and maybe even to begin with a theory of how human brains work. Now,
correct.
my first question is, I've got a few dollars laying around extra. How much can I pay you to buy Vicarious?
uh, yeah, yeah, we might be able to accommodate that. Yes.
Okay. Okay. So, in preparation, I'm extremely well prepared. I actually looked up the definition of vicarious just to make sure I had it right. And the definition is experienced in the imagination through the feelings or actions of another person.
Yeah.
So how did you come up with that name? And can you just tell me a little bit more about the company and your current role in the company?
Sure. Vicarious, the name. So this is also reflects our philosophy on how to build intelligence and what is intelligence. Vicarious, to experience something vicariously is to experience it through somebody else's eyes, and for that, one, you need to have a model of what that person is going through. You need to be able to model some other person, and should be able to see the world from some other person's viewpoint. And that means modeling is important. You have to build models, not just about the world, of other people in the world, and see the eyes through there. And that is the ultimate form of intelligence. And that's why we chose to name the company Vicarious. And it kind of reflects all our philosophy that models are important. It is not just pattern recognition, etc. So, as you mentioned, the long-term goal for Vicarious is to build human-level intelligence, and we are doing that by building an AI layer for robotics. And this is also important because we think understanding the world just like a child does. A 3-year-old child has a very good understanding of the physical world around them, can manipulate objects, has common sense knowledge about how to interact with objects, and has the concepts, the 3-year-old child has the mechanism to acquire concepts and to build language on top of it. For us, that is, in our way of thinking, that is the way to build intelligence. Start from the ground up, have a sensory-motor understanding of the world, and have it in a way such that you can build concepts on top of it. And that's why we are using robotics as the domain to drive both the products and the research in the company.
Yeah, I love in some of your talks, which I'll link to in the show notes. You give really nice talks, and you show like assembly lines, factory workers, just a crowded factory full of factory workers, 100 years ago, and then you show today, and it's still the factory workers, and the goal is to replace those factory workers with the robots. It's really nice imagery. Yeah,
the many of this work is very routine for humans. It is not challenging. It's pretty routine jobs, and it's hard for factories to actually find people and retain people to do these kinds of jobs. Some of them which might be dangerous, some of which are just repetitive and ergonomically not very convenient, etc. So, however, it's a problem that is still very hard for robots. It is still very hard to automate because you need some amount of common sense understanding of the world around you, so that when the problem structure changes, you can easily adapt to the new situation. So it needs a really powerful AI layer so that robots can adapt to these varying situations, which humans are really good at doing.
Very good. Well, so we're about to talk about one of your recent papers published in Science, but before we do that, what's something right now that Vicarious is working on that you're excited about?
Oh, everything. So we are we are working on the full stack in robotics, so that except building hardware, we buy hardware. So we use off-the-shelf hardware, but all the software stack we are working on all layers of that software stack, starting from perception and then closing the perception action loop, so that perception leads to good control, and then having another layer on top of that, which is learning concepts from these sensory motor interactions, so that you can actually convey a concept to a robot in a very, very simple way, in a more human-like way. So we are working all the way from perception and action to cognitive level.
And how much sleep are you personally getting these days?
I do sleep.
Yeah.
Sometimes I stay up late, but I catch up on.
Okay, good.
Yeah.
Okay, well, so I want to talk to you a little bit about the recent paper that was published in Science
Yeah.
called A Generative Vision Model That Trains with High Data Efficiency and Breaks Text-Based CAPTCHAs. So you and your team at Vicarious published this. Now, on recent episodes, have had guests and we've talked a lot about how deep learning might be implemented in the brain and how we can understand brains better using deep learning methods. But what you do isn't deep learning. You use what's called the recursive cortical network. It's a model I know with a lot of neuroscience-based features, and it performs well on a ton of tasks and benchmarks, including breaking CAPTCHAs. Now, I'm just going to explicitly define CAPTCHA. I'm sure everyone knows what a CAPTCHA is, but the word stands for Completely Automated Public Turing Test to Tell Computers and Humans Apart. So basically, it's these things when you log into a website or like download a file or something like that. It's that curvy text that comes up that you enter in that you have to prove that you're a human, essentially.
Correct.
And breaking a CAPTCHA in, I guess, the machine learning world is when a machine can automatically solve it at a rate higher than 1%. And so I have a really naive question, Dileep. So why is the 1% seems like a really low bar. Why is that so low?
Oh, because, if a machine can solve it even at 1%, you can just try 100 times and, you will get one right.
I see.
So it is low cost to try. So you can, a machine can easily get through just by trying 100 times. So 1% is kind of a bar that people have set as, okay, something achievable. Initially they wanted it to be much lower than that. They wanted it to be 0.01% or something,
right?
But that was not even achievable. So they took 1% as a number that is kind of achievable and still meaningful.
Oh, okay. Well, I told you it was a naive question. So, and it's interesting. You guys actually had solved this a few years ago, but you waited to publish because at that time when you had the technology to solve it, CAPTCHAs were mainly the text-based ones, like I just described. And so hackers and spammers could have used your technology to run rampant. But now a lot of CAPTCHAs use images, so there's less worry about that nefariousness. And you guys felt safe to publish it now.
Yes.
Also, I know you tested your model on a lot of different tasks and a lot of known benchmarks, and you tested against a lot of other models, and it excelled across the spectrum of tasks and other models. So for simplicity and time constraint, we'll focus on how it breaks CAPTCHAs.
Yep.
So why is breaking CAPTCHAs a good problem to work on, or why is it a good benchmark?
Yeah. So CAPTCHAs are, a very nice example for the generalization power of human brains and human vision. So I can show you a new CAPTCHA, which is created in a completely new style, maybe different clutter, different way of occluding letters, different way of filling in the letters, etc. And you would have no trouble understanding what that CAPTCHA, what the letters are, parsing out the letters from the CAPTCHA, understanding what the occlusions are, etc. If you think about it, it is miraculous because it is completely off the training distribution. You are mostly trained on clean fonts when we grow up, even if I show many of these CAPTCHAs to a 5-year-old child or 4-year-old child who have just learned to parse the characters, they can still parse the CAPTCHA without having to get any training data from that particular style of CAPTCHA. And this is not the way current pattern recognition systems work at all. If you need to solve a particular CAPTCHA, you need to give it lots and lots of training examples from that particular CAPTCHA in the same distribution, and then it will learn to parse that CAPTCHA. But if you change the distribution, even in terms of just moving the characters a little bit further away from the training distribution, the current pattern recognition systems will break. So CAPTCHAs in our mind, and it is true that it shows the generalization power of humans, that you can just train on data that looks completely different from the test data in terms of the distribution, and humans still do fine. And this is a problem that machine learning has to tackle if you want to go after problems which are more general AI-like. And that's why we took CAPTCHAs as an example problem to tackle. And I mentioned this in my talks. Douglas Hofstadter, who is one of the famous AI researchers and philosophers,
Yeah.
He had this quip that the central problem in AI is to understand the letter A.
Yeah.
And that is true. If you can solve the problem of what is the letter A, and if you can recognize the letter A in all circumstances, you have actually made a good amount of progress towards the general AI question.
So that's I'm making it a habit now to sort of come down on his famous book, Douglas Hofstadter's Gödel, Escher, Bach, and how it's way too long. But
Yes, there are other books which are more relevant for AI. I like the book. I think one was called The Mind's Eye or something.
Yeah, I think that was with Daniel Dennett, maybe.
Okay,
Yeah.
I like that book a lot, and so yeah, there are some. GEB is definitely hard for me to penetrate, but there are other writers from Hofstadter which I found to be much more useful for AI.
Yeah, well, I was going to say that statement about understanding the letter A is one of the most succinct things that I've heard from him. So that's that's good. Okay, so before we talk about the recursive cortical network, the technology that you use. So this is the brain-inspired podcast. So can you describe just a few of the principles from neuroscience that are included in the RCN? Should we call it the RCN? I don't know. What do you call it?
Yeah, we call it RCN, yes.
Okay. And so can you describe a few of the principles from neuroscience that are included in it and why it was important to do that?
Yeah, so we did use a lot of insights from neuroscience to design the representational choices of this model. And this is also tied with our overall philosophy. So if you think about machine learning problems in general, if you do not make too many assumptions, if you try to learn tabula rasa, just a blank slate, then you need enormous amount of training data, and it might not generalize from the training distribution. So you will be just capturing the training distribution, and it won't generalize. Whereas if you want to generalize to new things, then you have to make assumptions. You have to put assumptions into the model. Now, if you make too many assumptions, then you are building, a specific circuit for a specific problem. That doesn't generalize as well. So evolution through millions of years of experimentation has figured out this Goldilocks magical structure, which makes just the right amount of assumptions to be general enough, but at the same time it is specific enough so that you can learn quickly and generalize to distributions that are outside the training distribution. So that's the way we look at the visual cortex, and when we look at the whole cortex, we look at it to see what are the generic assumptions that we can get from this neocortex, that will make your model more specific than a tabula rasa model, but still very, very effective in solving a very broad domain of problems. So, for example, our model, RCN, will be terrible at solving QR codes. If you want to classify QR codes, our model will be terrible at doing that. Just like humans, if you try to show different QR code patterns to a human and ask them to recognize it as, they will be terrible. So that shows that the visual cortex is not a just completely general pattern recognition system. A deep neural network will be fine in recognizing these QR codes. So the brain is making some assumptions that doesn't let you model QR codes very efficiently, but lets you deal with CAPTCHAs and natural images very effectively. So that's the philosophy, with which we look at the neocortex. What are those assumptions that, lets you do this thing? And I can go through some of the properties that we observed from cognitive science and neuroscience and use those as representational choices in our model. One is this idea about factorizing objects and backgrounds, representing objects as different from the background. And then having this idea about object-based top-down attention. So even when objects are overlapping completely in space, if you have transparent objects that are overlapping, humans have the ability to separate out in a top-down manner oh, these are the features or contours belonging to object number one, and these are the features or contours belonging to object number two. And so you used something called top-down attention. So we took this idea that you have to be able to do top-down attention on these models seriously. So that brings in some constraints on what kinds of models can do that. Not all kinds of models can do this top-down attention. Another idea is the property about contours versus surfaces being represented on separate channels, but they do interact, but they are represented in a factorized way. And where this is useful is if I show you a chair made of ice, for example, and you have never seen a chair made of ice, you can still recognize it because you model the shape of the object separately from the appearance, whatever texture. I might paint it in a different color and you can still recognize it. So that's a property of the visual system that we wanted our model to have. So we put in a scaffolding in our model which lets it have this property. So those are examples of insights that we use from neuroscience.
Yeah.
And I have more. So I just wanted to see whether you have any questions on that.
No. I mean, that's a great place to start, I think. So, I mean, I know that there are a lot more actually.
Yeah. So another one is feedback. So this is a big one, So
yeah.
In the brain, while you are, doing recognition, feedback connections are just as active or more active compared to feed-forward connections. In fact, feedback connections are more numerous compared to feed-forward connections
Right.
In our visual cortex. And feedback connections are largely ignored in multi-level perceptrons or deep neural networks.
Right.
And so we asked, what is the role for these feedback connections? What is the computational property of? And people have studied this. Of course, people have studied it, saying that this is the feedback connections are part of doing inference, a Bayesian inference. So visual cortex is doing inference rather than just pattern recognition. And people have hypothesized the roles for these feedback connections. And for us, having the feedback connections was crucial. Without that, we wouldn't be able to solve CAPTCHAs with the data efficiency that we had. And we do give examples of this in the paper. So what often happens is that locally, when you look at part of the image in a complicated CAPTCHA, you can see letters that are created by combinations of other letters. And these are kind of spurious patterns that you will see if you look locally. So the only way humans are not confused by that is because you can explain away that evidence based on the presence of other letters. And this idea of explaining away evidence is inference. And this requires not just feed-forward connections, actually have feedback connections. And these feedback connections need to be active all the time when we are doing visual inference. So this was another crucial piece that it is well known in neuroscience that these exist, and people explain it from different angles, either Bayesian inference or predictive coding, etc. But this was one case where we concretely showed its use in a large scale visual perception task.
Well, so I have a neuroscience background. Plus, let's be honest, I'm just not that bright. So I found the paper. I found the paper pretty challenging, actually. So, and I have to confess, I got a little lost in some of the technical details and features of the recurrent cortical network model, the RCN model. So, do you want to just give a high-level description of the RCN and how it works?
Sure. So, it's easiest to understand if you have a background in probabilistic graphical models.
Okay.
But let me try to explain it in so maybe I can make a distinction between neural networks and graphical models, and that will anchor it.
Great.
So one way to think of neural networks. People are more familiar with neural networks now because of the deep learning revolution, and so an input to a neural network is always a pattern. It doesn't matter what the input is. The neural network will treat it like a pattern. It will treat it as a vector of numbers. And the output, of course, you can train it to mean, probability distributions or another pattern. So the input is always treated as a pattern. The output, you can train it to have semantics associated with them. You can say, oh, this number represents the probability of a particular class being active in the image. So in graphical models, it's there are no inputs and outputs. Like, every node can be an input or an output, and the inputs and outputs both have this semantics associated with them. They are all statements about something. So when I say a node in our model, the input to that is the number 0.9. That means it's a statement about that node being on versus off. The probability of that is 0.9. So at a rough level. And the second thing about the graphical models is that information flows in all directions all the time. It is not, so a graphical model you can think of is a set of states or random variables and the connections between them, which are modeled in these nodes called factors. So we have the random variable nodes and the factor nodes model the correlations or dependencies between these states. And once you have a network of these random variables and factors, then you can ask questions like, if I have more evidence for this pixel being on, which that pixel corresponds to a random variable, what will be the effect of, how will it change my belief that this image is a dog or a cat? You can ask questions like that. Or you can ask questions like, if somebody tells me that this image is more likely to have a dog or a cat, how likely, how does this change my belief on this pixel being on? So you can ask questions in many, many different ways. Or you can ask the question, if I have a dog in the image, how does it change my belief on a cat being also present in the image? So once you have, built this graphical model, you can ask it many, many different questions than, what you are, when you train a graphical model, you are training it to just model the data. You are not training it to answer a particular question. Then you can ask it then different questions during inference time. So that's, I just wanted to give that as a very simple tutorial on the distinctions between neural networks and graphical models.
That's great. Yeah.
And now our model, the RCN is a probabilistic graphical model. So you construct it, you train it to model the data, and then all the other questions, classification, segmentation, reasoning about occlusions are all questions that you ask this model after training. You are not training it to answer that particular question. And so how does it model images? So as I mentioned, so you do have put assumptions into the structure of the model so that images are constructed of objects and backgrounds, and objects are constructed of contours and surfaces. So these broad assumptions are there in the model. But what kind of features do you use for the contours? What kind of features do you use for the surfaces? Those are all learned from the data. But the idea that there are contours and surfaces as two separate things, and how they interact is an assumption in the model. So you structure these broad assumptions as a graphical model, and some parts of this structure are similar to the structures that we find in convolutional neural networks. For example, the idea that the contour features do local feature detection and then pooling, and then do again another local feature detection and pooling on top of that, and gradually build a feature hierarchy. That is somewhat similar to the structure that we find in convolutional neural networks. The difference is that, one, the features are generative. So it is not just discriminative features. You can take a feature at any intermediate level and sample from it so that it will generate all the way back into the pixel space. So you can associate features at intermediate levels with the patterns that they are associated with in the input. That is one difference. Another difference is that we also have lateral connections between these features. And lateral connections are important because, again, this is another insight that we used from biology. Lateral connections enforce contour continuity. So when you have features which are local, and when you pool over those features, you lose some amount of constraints between these features. So you can think of a horizontal line in one location and another horizontal line in a slightly translated location. And if you pool over them, then you lose the relative positioning between them. And lateral connections bring that relative positioning back and enforce some amount of contour continuity while also keeping the flexibility of these pools. So this is another insight that we use from biology. So the contour hierarchy is in some ways similar to a convolutional neural network in the structure, but in many ways dissimilar because of the generative structure and because of the lateral connections.
Right.
And then this contour structure interacts with a surface model, and the surface model is reasonably easy to understand. It's pretty intuitive. What the surface model is saying is that if I see a patch of surface in one location in space, I am expecting to see similar patches in nearby locations. So if I see a small patch and it is blue, then I am expecting to see blue patches as its neighborhood. And the way this surface model interacts with the contour is that I expect this to be similar, except when there is a contour in between. So, surfaces will be roughly of the same characteristics, except when there is a contour breaking their property. And so that's how the surfaces and contours interact in the model.
Well, that's great. And well explained. Thanks. So a major strength of the RCN is its efficiency. So most machine learning models, like deep neural networks and stuff, require tons of training examples. And the RCN achieved good accuracy with just 5 training examples, at least on the CAPTCHA data. So it achieved 66% breaking, I suppose. And whereas humans, on average, I guess, break the CAPTCHAs at 88%. That might even be high for me. I don't know. But so how does it achieve such training efficiency? Is it the inference that you were mentioning previously?
It's the combination of all the things that we have done. It is basically we have put more assumptions into the model. So we assume that there are an image is constructed of objects and background. That is an example of the assumption that goes in. We assume that objects are composed of contours and surfaces. So those two assumptions plus the way in which we do inference, it's a confluence of those things that leads to the data efficiency.
So so you keep mentioning the assumptions, and a lot of these assumptions that you build into the model are brain-based. But, I suppose the goal of engineering in general isn't to capture brain dynamics necessarily, but to solve problems. So I'm assuming that there are plenty of non-brain concerned assumptions in the model as well. So is there kind of a balance between those things, or what's going on there?
Oh yeah. It's so for example, we don't try to model all the things from we don't have we don't even have neurons in when we talk about our model and when we build it in software, we don't talk about neurons and spikes or dendrites or anything. We talk about random variables and factors between them. We talk about maximum likelihood as the learning mechanism, and maybe here we are using pseudo likelihood, here we are using maximum likelihood, and then we talk about message passing based inference. So this is another concrete idea which comes from the probabilistic graphic machine learning and probabilistic graphical model community, but it's very much connected to neuroscience. So we implement our inference algorithms using message passing, but the scheduling of those messages is actually very much inspired by what we observe in biology. So we don't try to replicate the details of the biology. We try to get the information processing principles from biology and put it into our model.
Okay, cool. What's something that the RCN is not good at? I mean, you mentioned the QR codes, right? So what's something else like maybe that's important that it wouldn't work with?
Oh yeah. So right now, for example, RCN will not be competitive on some of the standard classification benchmarks that we tested. For example, the ImageNet data set, and the reason for that is clear. It is not just a problem with RCN; it is also a problem with most generative models that will try to solve that problem. Because one, the problem is set up as a classification problem, and so it is straight set up for a system that is good at discrimination. And generative models will get good at that problem eventually, but they will have to solve it in a much more deliberate way. So when humans look at an image, you use the context in that image. You see a patch of grass, so you know that, okay, here is the ground, and now on grass, cows are more likely compared to some other object, some alien object. So humans use this context, but they use it in a dynamic and generative way. So we have to build all those things into our model. Of course, that is part of the research project that we are doing. But until we build all of them in a generative way into our model, and so that, because generative models try to explain the whole scene, and so what we did in the paper was being able to explain objects and backgrounds, but not any idea about a whole scene structure. So those have to be trained and put into the model. And once we do that, but that, of course, is a significant research undertaking.
Yep.
So being able to get to the level of what deep learning discriminative systems are able to do on ImageNet, like getting there is going to be a challenge for the generative models. But there are places where our models excel, even in the real world. For example, we tried on many of our robotic tasks where we need to pick up objects. So these are, objects that you don't get a lot of training data for. They occur in very cluttered bins. And we see that our system is very, very good at getting proficient at that with very few training examples.
That's great. So there are a growing number of labs, research labs at least, trying to figure out how brains can implement something like back propagation, the way that neural networks are trained.
Yeah.
So your model, the RCN, it has a backward pass in the model. Is that anything similar to back propagation?
Oh, no, not at all. So the distinction is the backward pass in our model happens during recognition. It is not something that happens just during training. So the backward pass is always on. It is always, it is required even during recognition. So this is like the feedback connections in the brain, which are active during the normal recognition hours. There is no separate training hours. So the mechanism that we use is called belief propagation. So it has the name propagation in it, but it's different from back propagation. It's still, it has lots of similarities in the sense that it is a local algorithm. You are just sending messages to your neighbors, and the neighbor is sending message back to you. So it is a very local algorithm which is trying to arrive at a global consensus. But it is doing something very different compared to back propagation.
Gotcha. Well, I know recently also, beyond this paper, you have, I know that this is just a work in progress all the time, but you've added some more constraints, biological constraints to the model, enough that you've tacked on the word neural onto the beginning, and now you have a neural RCN.
Yes.
So what further biological constraints does the neural RCN have, and how do they affect the model?
Yeah. As I mentioned earlier, the RCN model, when we build it for putting on our robots or as published in the science paper, that is purely explained using a probabilistic graphical model. So the whole model is explained in probabilistic graphical model terms, although the representational choices of the model, a lot of it, and also the inference dynamics of the model in how we schedule the messages, a lot of those insights came from neuroscience. Now, this mathematical model that we have can be mapped back into biology. So you can take the computations that we do in the model and then find a mapping between that and the cortical circuits. These are, the columnar and laminar circuits that we find in the visual cortex.
Yeah.
So we can basically find the correspondence between the computations that we do in our factor graph, the probabilistic graphical model, and the computations that happen in these cortical circuits. And how do we do that? Because we do know a lot about cortical circuits. We know a lot about the laminar organization. We know, column to column connectivity. We know which lamina connect to which lamina. We know where the feed-forward connections originate from. We know where the feedback connections come from. We know quite a bit about path through the thalamus. So you can think of these as pieces of a puzzle given to us. We know these are how the connect. This is how roughly the cortical sheet is connected. Then we can ask questions: what is the computational role for that? And can we explain those computational roles in terms of the model that we already built? Although the model is purely in factor graph terms, and the correspondence should exist because many of the representational choices that we put into our model did come from observing the biology part. So then what you can do is you can actually build a full cortical circuit which is elaborated in terms of columns and laminae, and that will be a way of instantiating these computations that we do in the factor graph in terms of neurons and columns and laminar organization. So that will be a functional canonical cortical circuit model. So it is different from the other canonical cortical circuit model in the sense that this cortical circuit model will actually do some function. It will recognize objects and fill in the missing pieces and etc. So it will do exactly the same thing as our RCN model is doing in recognizing these objects in complex scenes, but it will do it in a way such that you can find a mapping to the cortical circuits. And in addition, you can also go and reproduce some of these visual phenomena that we find in real brains. For example, the subjective contour illusions and neon color spreading illusion. These are all examples of visual phenomena that are well known, and these phenomena happen as the combined effect of feed-forward propagation, feedback propagation, lateral connections. All of them need to be there for this phenomena to occur, and we can reproduce many of those in our neural RCN model.
Well, Dileep, this is really nice work, and I'm looking forward to seeing what comes next for you guys. I know you're working hard.
Thank you.
So let's switch here, if you don't mind, to in our last few minutes here. Are you ready to get in trouble? I want to ask you for some speculative questions, some general questions.
Oh, sure. Also, you wanted to. You had a question about backprop in the brain, and So. As you mentioned, many labs are focused on this question of how does the brain do backprop,
right,
or if it does backprop.
Right.
Yes, and it's a good question to go after. From our perspective and my perspective, I am willing to take it for granted that brain can do backprop, but that just leaves us where we are currently. That leaves us just with our current techniques for building the systems. So while it is undertaking in terms of saying what can the current AI techniques, what might it teach about the brain, it doesn't help me go the other way. It doesn't tell me what insights from the brain can I use to build the next generation of AI systems. So I do think it's a worthwhile research question, but that's something I'm kind of taking for granted in some ways.
Yeah. Interesting. Yeah. Good. Well, so are you ready, Dileep, for some?
Yes.
Okay.
Yeah.
So what is something that you have been really wrong about or failed at in the past?
Oh, I don't know. I keep failing every day. I don't. So.
That's what everybody says. Okay. All right. How about this? What's one idea that you can't do, or you don't have the time or the resources or something that you wish someone else might pursue?
Oh my God. So lots of them, right? Oh, well, I don't know. I just want the time and resources to pursue it. I don't want anybody else to pursue it.
Okay. Okay. So it's secret.
That's a bad answer, but kind of the truth.
So from your perspective, sort of on the industry side, do you think that the trend is increasing or decreasing, or both maybe, to incorporate more neuroscience features into AI models?
Yeah, that is a mixed bag, I would say. Real insights being incorporated are rare. And I think people always like to, a lot of people always like to think about the brain. And there is also a tendency to kind of sell things as, this was inspired by the brain,
Right.
by putting in some stuff. One caricature I sometimes present snarkily in some meetings is that, oh, I can put a different non-linearity as at the first level of my deep neural network and call that the thalamus layer.
Oh, yeah.
So, I mean, those kinds of things actually do happen,
Yep.
So that is more like naming the different modules in the system as thalamus, and this is ventral stream, dorsal stream, those kinds of things. And yeah, they are kind of inspired by biology, but we are looking for deeper inspiration, I would say.
How possible is it, do you think, that focusing on the brain as a guide for developing general AI, that could actually limit our potential to go beyond that level of intelligence?
It doesn't, in my mind, and I explain why. So one, without using that as a human intelligence as a benchmark, there is no other example or existence proof that we have for intelligence. So we do have to use it as a benchmark to guide our development. And the question that I ask others, if you are not using that as a benchmark, then how do you know that we already haven't solved the problem? Because
Right.
because how do you determine that your system is not already AGI? And whenever you do that, you always compare with humans, saying
Right.
that, okay, look, it's a gap. And so we are of course using, even for people who are not willing to admit it, we are actually using human intelligence as a benchmark implicitly. So now, and as soon as you build something that is modeled after the human intelligence and benchmarked after the human intelligence, it will automatically go beyond it because it doesn't have the substrate limitations of human intelligence.
Yeah.
One, you can build it bigger. You can train it longer. It doesn't have to, it doesn't have all the other drives of humans that are distracting. So it can be really efficient in doing what it does without having to worry about survival and paying mortgages and taking care of kids, all those things. So it will automatically be beyond human level.
I'm gonna just skip the joke about my wife finding some of my drives distracting. So okay. So here's a big one that you might want to skip. So how does consciousness fit into the long-term story of building general AI? Are you worried about it? Is it something you think about?
So consciousness is, in my thinking, modeling. It's self-monitoring and modeling yourself. The modeling power that we are using to model the external world, you can turn that same system on the models that you are building, so that will build you a kind of self-monitoring ability. And if your model is powerful and it's sophisticated, that self-monitoring ability will start to feel like consciousness. That's my thinking about it. And yeah, so, and as we build these systems, self-monitoring capabilities will become more and more important. And we see this all the time. Even when you're in robotics, you kind of see this. You have to build it from the very beginning. And as your model starts becoming more and more complex, the self-monitoring capabilities also will become more sophisticated.
Yeah.
And to me, that is consciousness. You don't do something too different.
So there's no magic in there.
Yeah.
Okay, so I ask this sometimes at like parties. Not that I get to parties much anymore, but so I think we can safely say that as a species, we're kind of embarrassed at this point about slavery. That's wrong, and so we can look back and say, oh God, that's kind of embarrassing that we ever did that. Things like that, women's suffrage, things like that. What do you think? What do you have something? What is something that, as a culture or a species, do you think that our generation are doing right now that we will be collectively embarrassed by? And this can be in the realm of science, neuroscience, or just in general.
Oh, lots. I mean, this will get into politics and.
Well, yeah. Okay. that was low-hanging fruit, but.
Yeah, it's climate change. I hope we can do a lot more about it, and a lot of our entrepreneurship can be directed in that to attack that problem. I do have several friends who are running companies which are trying to tackle this problem that is going to face us head on, few years down the line. So
that's good.
So that's an example of a problem where we should be all collectively embarrassed that we haven't got our act together.
Okay, that's a good answer. So if you had to be frozen and then thawed in the future, when would you want to wake up and why?
Oh, I don't know. It's a question of am I frozen with other people or is it just me?
Damn it! I can't be that specific with these questions, man. Right. Okay, so I'll take tomorrow because life is good for you right now, I think. So
yeah.
Hey, so Dileep, what can we expect from Vicarious in the next year or two?
Well, one, definitely products. We are pushing some of our work into products and doing real life deployments. So one thing very rewarding for us would be when our products start getting used in the real world.
Yeah.
And seeing something being used, that is very rewarding. So that is one thing. And we are working on some cool ideas related to how higher level concepts can be learned. We hope to see some of those, getting published, and those ideas getting discussed. And also we hope to see some of the things that we kind of championed, in terms of data efficiency, causal generative models, and using insights from the brain in a deep way, being taken up by the broader community.
Well, I'm looking forward to it. So my last question here. So this whole podcast has been a ruse, really. So can I skip the whole applying for an interview, and can you just hire me now, or
please do.
Okay.
Please apply for. We are always looking for smart people. Yeah. So
okay. Great. Now I don't have to blackmail you. That's good. So, well, thanks a lot, Dileep, and continued success to you.
Thanks, Paul. It was a pleasure talking to you.
All right. I hope you enjoyed that departure from all the deep learning talk that we've had lately. Next week, I will have Conrad Kerding on the show, and hopefully pronounce his name right at the time. And we'll talk about a lot of things. He's a bit of a polymath. All right. See you next time.